Good morning, everybody. We have been talking about alkenes. My voice is almost back, but not quite, so hang in here with me. We talked about naming alkenes, and now we need to talk about some of their properties. An alkene can do something that is unique to alkenes compared to other alkane equivalents, which is they have cis-trans isomers. So I'm gonna put two sections together. 7.4 and 7.5. So they really should just be one section. It's going to talk about cis-trans isomerism. All right, if I have something like ethane, that is a CH3 attached to CH3, I'm going to highlight two of the hydrogens, one here, one here. We spent a lot of time talking about how I can rotate around this bond freely. So spinning around that bond leads to what's the name we use for a molecule that looks like this versus that? Staggered and eclipsed are conformers of each other, right? So we know that I can freely spin that molecule to put those two hydrogens on the same side. So the hydrogens were anti to each other. Now the green hydrogens are eclipsed. Actually, all the hydrogens are eclipsed, but the green ones are obviously eclipsed. All right, so there is what we call free rotation here. So we wouldn't refer to either one of these molecules as isomers. We would call them conformers because it's the same molecule that's just moving around. If I put a carbon-carbon double bond into the mix, I have those hydrogens stuck on one side of the molecule. Good morning. These hydrogens cannot freely spin. There is no free rotation here. Which means when the hydrogens are both on the same side of the molecule, they will always remain on the same side of the molecule. If the hydrogens are on opposite sides of the molecule, they will remain on opposite sides of the molecule. This leads to a three-dimensional orientation difference between the two, which is stereochemistry. So we need to start referring to alkenes based on, are they like this? Put the pen down. Are they like this, where the two groups are on the same side? Or are they like this, where the two groups are on the opposite side of the double bond? My thumbs are the double bond, right? For alkenes, we're going to use E and Z, even though cis and trans also works. Cis and trans is like an umbrella term. E and Z refers specifically to alkenes. And I'm just going to go to a new page for this. Does this make sense? If you have an alkane, you can freely spin, right? Single bond, no problem. If you have an alkene, you can't freely spin because now there's a pi bond involved. So I'd have to break the pi bond and then reform it. Right, so there's no conformer to do this. That is a chemical reaction to do this. If I have a single bond, freely spin, no problem. Like the way we used to tease people, like the way some of our younger guests might tease people in class, right? Be nice to your friends. KASSING, anybody? Yeah, a couple of you. The bullies in here. Something about doing it in a tree. I've never understood that. I've never kissed anybody in a tree. Maybe I haven't lived a very exciting life. Let's talk about E and Z designations. Some of you are like, what is he having a stroke right now? What is he talking about? Okay, what we're going to do is we're going to use Cahn-Ingold-Prelog rules to decide if the high priority groups are on the same side of the molecule or on opposite sides of the molecule. We're going to use CIP rules. Cahn-Ingold-Prelog rules, just like we did whenever we were doing our stereochemistry for chapter 5. Same rules apply here. Okay, we have two different designations here. If my high priority groups are on the same side, and what I mean by this, SIP rules to determine priority. So if my high priority groups are on the same side, that would mean my low priority groups are on the same side as well. We are going to call this E geometry. And the way you say that functionally is you would just say that is an E double bond, or that double bond has E geometry. I forget, does anybody speak German in here? I think I've asked this before. No one sprechen Sie Deutsch? Good, then I can butcher it. This comes from our German colleagues for the, you don't need to know this, but in case you're interested. This comes from the German word Eintgegen. I think it's actually, if I've had students who spoke German in here, I think it's actually Entgegen or something. I don't know. I say Eintgegen, which means opposite. Eintgegen, opposite each other. If the two groups, wait, why am I doing that? I screwed this up. You're probably wondering, those are not opposite, those are on the same side. Hi, my name is Nathan. I teach organic chemistry. This is Z geometry. Sorry. Nobody was like, wait a minute. Something is wrong here. Something is not right. Okay. Hold on to that. It's coming back. These two groups are on the same side. I was like having cognitive dissonance as I was writing this out, like, yeah, so now they're gonna, oh, no. Okay, this word comes from zusammen, which sounds like ramen to me. Zutz, make sure I get it right. Zusammen. Zusammen in German means together. We're having class zusammen, you know. We could go get some ramen zusammen, you know, it's whatever you want. My voice would really appreciate a nice bowl of ramen right now. All right, so the two high priority groups are on the same side, Z, or the two high priority groups can be on opposite sides. Okay, so now my high priority groups are not on the same side, they're on opposite sides. So this one would be E geometry. And I will rewrite it, but you know why. Eintgegen means opposite. So I have given you the etymology of where these words come from, and you're probably thinking to yourself, Dr. Green, etymology is neat and all, but that's not helpful because I don't speak German. But I bet you can put on a pretty good fake German accent. I have been working on my fake German accent for a while. And this is how I remember the E versus the Z, and if I had a better voice, I'd forget better. So I do not speak German, but I can do a really hooky German accent. And I think if the two high priority groups are on the same side, that would be Z. The same side. Yeah? Yeah. It's the dumbest thing ever, but it works. I have students come back years later and they're like, the same side? Everybody uses it. I like to just really draw out the accent though. If the two high priority groups are not on the same side, it's the other one. I don't know. I don't have a thing for E. The same side and then E, the other one. And then E. Are there any questions about the same side or the opposite sides?
I would just like to understand about the energy level. You know, like,
Oh, we will get to we'll talk about, it's not high energy or low energy, it's priority. If the two high priority groups are on the same side, then it's a Z geometry. That is going to have an impact on the stability, but we'll talk about that in a second. Yeah, so this is just for naming. Colin. So if the high priority group, if this one was down here. Oh, yeah, so you have to have different groups in each one. So you gotta, to Colin's point, you don't need to draw this out, but Colin's wondering if I have high priority, low priority, that's neither. That is very confusing because you can't have the two different groups. They're on the same side, right? So if you switch them, there's no difference in the isomer. We need to have, so your hands actually make a pretty good model for this, right? So everybody give this a shot. Carbon, carbon, make a double bond, right? So you're looking at the double bonds now. Put your fingers up. Now you're playing a little paper football game, right? Your fingers are, let's say, methyl groups. The two methyl groups are facing on the same side. They can both be up, they can both be down, but it doesn't matter, right? They're on the same side. If you break the double bond and twist it and reform it, now your fingers are on opposite sides. This is E orientation. This is Z orientation. Ja? Das ist gut. Das ist gut. Wunderbar. The way that you'll see this used, I know it's dumb, but it works, I promise. The way that this, and it's probably like a little bit racist too. I'm not sure. I don't have like any German students in here. So if you have German heritage and I've offended you, I apologize. Here are a couple different groups attached to an alkene. All right, I've drawn this in a funny way, but this is a butene, right? So there's 1, 2, 3, 4 carbons. It is a 2-butene because the double bonds at the second carbon. You normally wouldn't draw it this way. There's also a chlorine there, so it would be 2-chloro, 2-butene. 2-chloro, 2-butene. We see that? 1, 2, 3, 4 carbons, but. 1, 2, that's where the double bond starts, butene. 1, 2, that's a chlorine, although it looks horrible. 2-chloro, 2-butene. So then the question you need to ask is, well, dear professor, which one are we using? Right? Are we going to have the double bond be an E or a Z? So what we need to do is figure out, we'll split the double bond in half and figure out who's high priority on each side. Let's look at the left-hand side of this alkene first. Is the hydrogen or the methyl group a higher priority? The methyl group is the higher priority. On the right, so I'll just put a red circle in it. On the right-hand side, is the higher priority a chlorine or a methyl group? A chlorine. So this molecule, this E2-chloro-2-butene is E. Because those two high priority groups are not on the same sides, they are on opposite sides, E. Does this make sense? It's funnier when he has a voice. It's kind of funny now too. I went to a reception for the new president last night, and it was in the loudest possible room, Arts at 302 on Broken Arrow. Super cool place. But everybody was like having to shout to each other. So my voice was just done. And by the time I got home, it was like maximum puberty situation. So I was like, everyone have a good day. And Gabe was like, what's wrong with you? So that's actually an improvement of where I've been at. All right. We got that. That's too easy. Let's kick it up a notch. Samara had a good question about, all right, so we have these Z and E isomers, but is there any difference in the energy between those two? There is. There are actually two factors that impact alkene stability. One is isomerism, and the other one is substitution. We'll take on the isomer version first. Which one of these two alkenes do you think is more stable? This one or that one? That one. Why? Yeah, so this is like a steric argument, right? When you're like this, fingers are up here having a hard time. Let's pretend it's like this, right? Really bulky things, right? I got two mooses on either side of this. If I make the E version of this, I'm spreading out all the density around that alkene. For that reason, E alkenes are typically more stable than their Z counterparts because I just have too much stuff up here. This is crowded. It's a good way to catch a football maybe, but it's not a good way for an alkene to sit. E alkenes are more stable than than corresponding Z. Now keep in mind, you can use cis and trans here. So an E alkene would also be called cis. Nope. Trans. I'm having a hard time today. And a Z alkene would be called cis. So cis and trans do work. E and Z are preferred for alkenes because E and Z only refer to alkenes. Remember, we used cis and trans when we had rings, right? Things could be cis or trans on a cyclohexane. Things cannot be E or Z on a cyclohexane. E and Z tells you I am talking about an alkene. I want to show you an experiment that we use to determine this because I think it's important. This thing I'm going to show you has for years confused students, and I keep telling myself I'm going to stop talking about this, but I think it proves an important point. When I want to talk about the stability of a molecule, I don't just like look at this coffee and go, yeah, it's pretty stable. And then I look at a different cup of coffee and I'm like, oh, that's not stable. That's not good, right? I have to be able to measure the stability of these things. And we can't just like smell it or even like necessarily burn it so easily and tell the stability. We have to be able to run an experiment and measure the energy differences coming off of the experiment. So let me run an experiment for you that you have not seen yet, where I'm going to start with two different alkenes, I'm sorry. I'll have one where the alkene is E. And what I'm going to do is I'm going to remove that double bond. By adding an additional hydrogen. So we'll see if the colors are helpful here or not. You don't need to know this reaction yet, but it's going to become important for us. This type of reaction is called a hydrogenation reaction. So I'm going to add hydrogen gas. And then as a catalyst, I'm going to use a precious metal, something like platinum or palladium, which are really expensive. So what I'm going to do is take my platinum or palladium and I'm going to dissolve it and plate it onto a fine particle of carbon. The way you refer to this is platinum on carbon. And the idea behind that is this is not platinum. I am not that fancy at all. This is white gold, which by the way, white gold, very little gold in it. This is cheap. But if this was platinum, it would be worth a whole bunch of money because platinum is crazy expensive right now. If I ran my reaction on my ring, only the surface of the ring could react. But there's some weight to this ring, right, where I have a lot of platinum that would be in here that would be non-reactive. So it's a much smarter idea to take my ring and grind it up into little pieces, or in this case, dissolve it, and put it onto something with super high surface area. So it's not just the edge of the ring that's doing the reacting, it's all the platinum in the ring that could be doing reacting. That's what carbon is doing for us here. It's making the amount of metal that we need reduced so we can get the most bang for our buck. Don't worry about this too much just yet, but what's going to happen is my double bond is going to go away and I'm going to turn this into butane. This is a really fancy looking butane, but all I've done is remove the double bond and added hydrogen to it. This reaction is called a hydrogenation reaction. So let's think about what we've done, because we just got done talking about energy differences here. I broke a pi bond, carbon-carbon pi bond, and I made two new carbon-hydrogen sigma bonds. How do we feel about that energetically speaking? If I break a pi bond and form two new sigma bonds. Now the single bond's still there, right? So broke a pi, made two new sigma. Is that good math or bad math as far as the reaction is concerned? It's good math. A pi bond is relatively weak. Now a double bond is stronger, but I'm only breaking one of the bonding interactions, right? There's still a carbon-carbon bond here. So I'm breaking just the p orbital interaction on these carbons. If you remember back to way back in this class when we talked about pi bonds, we said that double bonds are stronger than sigma bonds. Or I'm sorry, double bonds are stronger than single bonds, but the pi component of a double bond is relatively weak. So I'm breaking a pi bond to make two strong sigma bonds. That is downhill in energy, which means this reaction is going to give off energy. We call that the heat of hydrogenation. The delta H, so that's the heat change of hydrogenation. This type of reaction is a hydrogenation. The heat of hydrogenation here is negative 116 kilojoules per mole. What's the negative tell me? It's exothermic, it's giving off energy. Fadi, what does this recommend is going to happen with our delta G? Is it going to be negative or positive?
Delta G.
Delta G, yeah. Is this helpful for our delta G or not? It's helpful, right? Because a negative delta H is going to help our delta G, which means this reaction has a good chance of being spontaneous. And indeed it is. We can get it to run pretty easily. All right, so we give off 116 energy units per amount of stuff that I run here. I can run this same reaction with the same reagents on not the E isomer, but I could do this with the Z isomer. So this molecule is E2-butene. This molecule is Z2-butene. When I run the reaction over here, my delta H of hydrogenation is equal to negative 120 kilojoules per mole. So I got more energy out of hydrogenating the Z double bond than I did out of the E double bond. So what does that tell us about the relative energy levels of these two alkenes? Are they the same starting energy, or is one higher in energy than the other?
The Z is higher.
The Z is higher. Very good. All right, so what's going on here is there's a reaction coordinate diagram, right? I will be the reaction coordinate diagram. Left-hand side are reactants, right-hand side are products. We have two different molecules. They're going to fall to butane. Butane is the table over here. So the question is, if they both start at the same energy, they will both fall to the same energy level and the same heat will come off. But if one of them is higher in energy, it will fall further and give off more heat. So we can use the heat of hydrogenation to say, hey, this guy over here gave off 120 kilojoules. It must have started at a higher energy level because when it went to products, it fell further. This one was lower, so when it went to products, it fell not as far. We can use that heat of hydrogenation to tell us about the potential energy of a molecule. I'll draw that out, but does that make some sense?
Is that because the Z alkene is less stable?
It means that the Z alkene is higher in energy, or in our vernacular, less stable. So here is the reaction coordinate diagram that I just very poorly acted out. That's my idea of a right angle, apparently. Let's try again. There we go. First try. All right, over here, I'm going to make butane. In both cases, I made butane. Butane's butane, common product. On my E, not my E, My E alkene, I went from here over some activation barrier to make the butane. For my Z double bond, I started up here and went over a barrier to make that. So my E double bond didn't fall as far as my Z double bond did. And that energy difference can be measured by the heat coming off of the reaction. The Z double bond is higher energy. Which means less stable. Gonna be a little, does that make sense? You see how I'm like connecting back to the stuff we used to talk about? And you were like, that thing is stupid and I'm never gonna use it and I don't like you. And I get most of that, but we used it, so you can still not like me, but hopefully it makes sense why these things are important. I forgot about, I really need to put this in my notes. This is a Dr. Green original, super nerdy joke. Tell me if you get it. What's the name of that molecule? One? Oh, no. Okay, so it's got a double bond. Is the double bond E or Z? It's E, right? The thing's like, it's like trans. It's not like, I didn't draw it like this. Right? That would be like that'd be like a Z double bond. So that's an E double bond. Where is the double bond? On the second letter. Anybody have a good AP literature teacher in high school? Oh, come on. Nobody's read Shakespeare, Caesar? All right, we got to learn about Shakespeare for a second. Okay, so Julius Caesar was this like emperor of Rome, right? He got like all power crazy and he went nuts. So he went out and he was going to try and overthrow the Roman Empire. And on his way into doing this, all the Roman senators were like, we don't think that's such a good idea, Caesar. So when he goes to address them all, they hatch this plot and they all stab the dude. I'm sorry, they make him hurt in his belly. So Caesar has a best friend. His name is Brutus. In Latin, Brutus is Brute. So the last senator that's going to come up and punch Caesar is Brutus. And Caesar says to Brutus right before he dies, and you, Brutus, which translates to et tu, Brute, or e tu, Brute. Right? So it is both a chemistry joke and a literature joke. And you are better people having heard it, even though it is really, really specific. Kylie, it's going to be funny later on, I promise. Not right now. Everyone go read Julius Caesar by William Shakespeare over the weekend. It's a page turner, let me tell you. Nobody's okay. Nobody has read Shakespeare. Or sorry, let me put it this way, right? Read Shakespeare. I also read Shakespeare, right? I read Frankenstein too, and I was in class and they were like, does anyone have thoughts? And I was like, oh yeah, the Frankenstein is just misunderstood and he wants to be a human, but he is torn between this world of being a monster and being human. And my teacher was like, Nathan, Frankenstein's the name of the professor, not the monster. The monster is called the monster. And I was like, I didn't read the book. Sorry. Anyway, there's my super nerdy. Now you can tell why it's a Dr. Green original, because it's lame and very, very specific. For those of you who are big into social media, go make E2 Brute big. Just blow it up. I don't even need credit for it. Double bonds like this are not as stable as double bonds like this, right? E double bonds are more stable than Z double bonds. The other feature of double bonds that we're going to be worried about is that more substituted double bonds are more stable. If you liked my classic literature references, you're going to love the really complicated explanation here. There's two reasons for why a more substituted double bond is more stable. The first one is the hardest, and it's called hyperconjugation. Hyperconjugation is the overlap of a pi bond with a neighboring sigma bond. What I'm going to do is draw just a piece of a molecule. I'm going to draw a carbon-carbon pi bond, and specifically just the pi bond. I'm going to leave out the sigma bond because it gets complicated. And then next door, I'm going to draw a carbon-hydrogen sigma bond. And we're going to see how this carbon-carbon pi bond is going to overlap with this carbon-hydrogen sigma bond. Okay, so carbon-carbon pi bond looks like this. That's the sigma bond between them. Don't worry about it. A pi bond is what orbital overlapping with what other orbital? Carbon. Yeah, what is this? Besides hang 10, right? P. P orbital here and a P orbital here. Note to self, hand signal is working a little bit, but not sticking with like the actual thing, right? So this is a P orbital on this side, that's a P orbital on this side. The picture on the screen is what that looks like. They would need to be phased together so that a P orbital on one side can run into a P orbital on the other side, and that makes a pi bond. Okay, that is this part, the pi bond. With me so far? Next door, there is a carbon-hydrogen sigma bond. Now this carbon is going to be sp3 hybridized, which means I need to give this carbon an sp3 orbital here. All right, so that's an sp3 orbital. And then the hydrogen has an s orbital. And that makes this thing a sigma bond. And apparently I'm putting everything in red because I forgot I had color. All right, so just focus on this part. Do we see the sigma bond, sp3 hybrid orbital on this carbon, overlapping with an s orbital on that hydrogen? All right, so I've got two bonding interactions, carbon pi bond, carbon hydrogen sigma bond. This would have to be overlapping as well, because they have to be phased together. So I want you to look at the screen, and for some of you, you don't need to squint too much, but if you can see this clearly, I want you to go like this. Look at it. It's gonna look like, if you squinted this enough, it kind of feel like pi bond, and then doesn't that kind of look like a pi bond there? Yeah, like you could almost like smear out the electron density from that side to that side. You squint and turn your head to the side, you could probably like force yourself to kind of make a pi bond to the next bond over there. The molecule feels the same way. That's called hyperconjugation. The carbon-carbon pi bond sitting there, and it's like, hey, you kind of look like me. You're not like me, but you kind of look like me. Would you like some electron density? And the carbon-hydrogen bond's like, well, I'm not like you, but we can be buddies. We're kind of nearby. This thing is hyperconjugation. A pi bond is conjugated. A p orbital running into a p orbital is a conjugated bond, a true conjugated bond. This interaction is trying to make it work, right? It's not working, but it's trying to make it work. And sharing more electron density is helpful because the more we share electron density, the happier the electrons are. The happier the electrons, the more stable the molecule. So if we have carbon-hydrogen bonds near pi bonds, the pi bond gets more stable. The whole molecule gets more stable. Make sense? Does it make this much sense? Okay, the other one is bond strength. I'm going to draw butene with the bond in the middle. And I'm going to draw it in kind of a funny way, where it's all spread out here. This is not how we would draw an alkene with proper bond angles, but here's 2-butene, not E2-brute. We didn't like it, by the way. That was like a wholesale rejection of my nerdy classical reference. And this would be 1-butene. So 2-butene. Double bonds in the middle. 1, 2, 3, 4. 1-butene over here. I brought up orbitals. I'm sorry I did that to you. I got to bring them up again. What's the hybridization of this carbon? sp3. Hamza, what's the hybridization of this carbon? I agree, sp2. What's the hybridization of this carbon? sp2. And hybridization of this carbon? sp3. All right. We talked about in chapter like 2 or maybe 3 that covalent bonds are good, but polar covalent bonds are even better, right? So if I have a carbon and a carbon sharing a bond, that's great. That's a covalent bond. That's a strong bond. But if I had a carbon and an oxygen bond, that's even stronger because the oxygen pulls on the electron density and it makes one of the species electron rich and one of them electron poor, and that further pulls them together. Right? So polar covalent bonds are stronger than just normal sharing covalent bonds. An sp2 hybridized bond is purely covalent. An sp3 sp2 hybridized bond is a polar covalent bond. And the thing I'm trying to figure out is where I'm going to put this on here, but you might be wondering, Dr. Green, please stop with all the weird references and maybe just stop talking about chemistry today, but why is an sp3 sp2 hybridized bond polar? Because these two carbons have different electronegativities. And the reason for that is if we look at sp3 versus sp2 versus sp, I want to talk about the S character of each one of these. And what I mean by that is if you're an electron around a carbon, you want to be in an S orbital, right? So if this is the nucleus of the carbon, you want to be in a sphere surrounding that carbon. S orbital is the bee's knees. That's a place to be. A p orbital is not as great, right? Because a p orbital, you're above or below, but you're not right where you want to be. So the more S character that you have, the more S-like you are, the more closely held you are to the nucleus. An sp3 hybridized carbon is 1 part S and 3 parts P. So 1 in 4 parts is S, or what we would call 25% S. sp3, 4 possible parts there, 1 S, 3 Ps. 1 in 4 or 25% S. How much S character to an sp2 hybridized carbon? 1 in 3, so 33.33333% S. How much S character in an sp hybridized carbon? 50. 1 out of the 2 parts, 1 S, 1 P, 1/2 is S. You're an electron. Everyone be an electron. You're very negative right now. Some of you more negative than others. Be an electron. Do you want to be in an sp hybridized carbon, an sp3 hybridized carbon, or an sp2 hybridized carbon? You want to be in sp, right? You want to be in an S, but I've removed that option. So you have to be in one of those hybrid orbitals. You would rather be here in the sp hybridized because you are most like an S. You are closest to the nucleus. And if you're an electron, that's where you're happiest, right? For that reason, sp hybridized carbons are more electronegative. Sp hybridized carbons pull their electron density closer to them than an sp3. So when I have an sp3, sp2 hybridized bond, that's polar because those carbons aren't sharing the same. Well, this is so technical, I know. But you know what this whole class is, so you guys are fine. What am I making excuses for, you smart cookies? Over here, how many of these sp2, sp3 hybridized bonds do I have? What's the hybridization of this carbon? sp3, that one. Also sp3, that one. sp2, that one. sp2. I feel like a glee conductor for like a prison right now. I'm like, all right, everybody ready to sing? And you're like, yes, we're ready to sing. You're like, okay, let's do this. And you're like, I don't want to do this right now. How many polar bonds are in this molecule? 1. How many polar bonds are in this molecule? 2. Polar bonds are better than non-polar bonds, right? More substituted alkenes are more stable because of it. So let's put this nightmare of technical reasoning into a list that is easier to memorize and deliver on. Before I clear this screen, any questions about anything on here? Okay. We're going to have 1, 2, 3, 4, 5, 6 alkenes. So let's put up 6 carbon-carbon bonds here. 1, 2, 3, 4, 5, 6. All right, what we're going to do is feed this thing carbons. If I have 1, 2, 3, 4, R equals a carbon, by the way, 4 carbons on there, this molecule is going to be tetra substituted. It is going to be the most stable. It's number 1. The next most stable alkene that we'll have is a tri-substituted alkene. It's going to only have 1, 2, 3 carbons on it. One of those is going to be a hydrogen. This is a tri-substituted alkene, and it is not as stable. Actually, maybe this is probably, I'm going to not put these numbers up here, right? Because I'm saying tetra substituted and putting a 1. Is that going to mess with anybody? Here's what I'm going to do. This is the most stable on this side. It's going to go like this. This one's going to be the least stable on this side. Okay. Now we're on to our di-substituted alkenes. I need to be careful where I put these R groups. Because remember, the most stable alkene is going to be the E alkene. So the R groups need to be on opposite sides of each other. This is di substituted E. I think Khaled brought up earlier that what if you have a di substituted alkene, but they're on the same side of the molecule? That would look like this, right? So the R groups could switch, or in this case, the hydrogens could switch. There's no E or Z there. This is di substituted as well, and it's really about the same stability. They're roughly equivalent, depending on what's going on here. This could be a little less stable. Either one of these are definitely more stable than if the two R groups are on the same side. This is di substituted, but the two high priority groups are on the same side. And that is more stable than if I have only one carbon attached, which is mono substituted. Are there any questions or reactions from the group? You have a quiz on Monday. You want to see how I'm asked questions about this? Of course you do. Hi, Maya. I'm just telling you in advance. I love to do this where I draw a structure that looks very similar, and then I go through and I put double bonds in different places. So I'll put a double bond there, and a double bond there, and a double bond here. Rank those alkenes according to stability. Who's number one? Grant, which one of these is the most stable alkene? You can't loiter if you're not going to be part of class. Class help Grant out. Which one's going to be the most stable? I've heard all the answers. You're all partially wrong. I mean, you're all partially right. That's glass half empty sort of answer. Let's do it this way. Which is this mono, di, tri, or tetra substituted? This is a tri substituted alkene. That's my alkene. I have 1, 2, 3 things attached to it. So this is a tri substituted alkene. How about this one? There's my alkene. I have 1 thing attached to it. It is mono substituted. How about this one? I'm blowing your minds right now. There's just like brain matter leaking out of the ears. Di substituted. Which one of these is the most stable? Most stable. Which one of these is the least stable? Least stable. I'm in the middle. Have a wonderful weekend. I will see you all on Monday for your quiz.